bunch of solvables NP problems. If you remember the Venn diagram I showed before, NP was the big blob. And we will be theoretically able to solve quite a few of these problems, given that we figure out the algorithms for them using a quantum computer. So that goes from making database research extremely fast. Now everything is like all our information, all our data are getting into computers. They are in the database stored somewhere, and it can get very tricky to find one quickly. A quantum computer can do that extremely fast. There's the Postman problem. How can you go from a point A to a point B going through every single intermediary point? Like say, if you wanted to visit the whole of South Africa, you wanted to go, say, from Johannesburg to Cape Town, but going through every single city. This is an impossible problem to solve right now, but this computer can do it. Volume maximization, if you have a specific space, a whole bunch of objects, and you're trying to figure out how to put this object in there so that it's all full, so that we're using the less amount of space. That's also an NP problem. That's something you can do right now, but that you might be able to do. But the application that I personally find the most amazing has to do with randomness. Is tossing a coin random? I think it's the output of tossing a coin, a head or a tail. Is it random? What do you guys think? Why? Why? If yes, why? If no, why? Yeah?
There is a cause to everything.
Was the answer yes or no?
It means no.
Okay. It is not random. Because if you were to know exactly the conditions that are surrounding you flipping the coin, if you could know the force that you're applying on the coin, the angle at which you're applying it, etc., you could predict exactly if you're going to get a head or a tail. This is randomness born from the lack of knowledge. It's not really sheer random. Right now, these computers can't emulate a random process. We can't have something completely random generated by computer. Even random number generators, which are basically a software that will give you a random number. And it's a lot more useful than it might sound. Even they are not really efficient. They loop. If you keep using that process over and over again, you will see a pattern. It's not really random. And having an access to a computer that can really emulate that randomness would be useful in many fields, mainly quantum physics. So basically, quantum physics, as I said before, revolves a lot around probabilities. Things happen at specific percentage changes, etc. And theoretically, if we were to build a quantum computer using these very particles, we could emulate the way these particles behave around us, the way subatomic particles work, the way, like, the most important, like, the breakstones that are used to build our universe really behave. So, scientifically speaking, this is fairly important. We're all about understanding how our world behaves, and this is actually a limitation that in chemistry, physics, biology, once things start becoming smaller, you're lost. You don't know exactly what happened. A quantum computer could build a mathematical model that is efficient and can really emulate that. But that's not knowledge for the sake of knowledge. It also has application. The next big thing is going to be very small. Would that be microfibers, nanotechnology using architecture, nanorobot that could get inside your body and heal your cells, like chips of a most conventional nature that will still operate on phones or whatever in the next couple of years. All these are getting smaller and smaller, and at that scale, getting a strong understanding of what quantum physics is all about, of how all these particles behave, can become critical into having an efficient and potentially usable design. And just Google nano, and you will see how many fields are interacting with it, how many fields will benefit from all this knowledge about the tiny things about our world. So finally, I just have like a couple closing remarks after that research that I spent a year doing. Computer science, school of science, but it's really something that we made up. It's something that we designed. We created computers, and we are right now trying to explore how they work, etc., how to push these things. And we have been using a lot, like, I'm saying computer scientists have been using a lot of input from physics, from chemistry, from biology, etc. And now with quantum computers, they can actually give back to all these sciences. They can actually take them all to a completely new level. And now I'm not saying that so that all the excels here can take pride of it, or computer scientists can take pride of it. But I think we should all take a bit of pride on this thing, because it's something we completely designed without realizing how deep it can go, without realizing how useful it will turn out. And it might actually just change the way we will be living in the next decade or so. And that will be it for me. Thank you. Also have time for 2 questions, so yep.
We're talking about earlier on in the presentation about the size.
Speak up.
Okay. You were earlier on during your presentation, you talked about how you would put 1,000 atoms together, and you mentioned how small it was, but then the capacity that it had. And I just want to ask you, when you're talking about the quantum computer, if we could manage to make something like that, how does that affect the hardware, i.e., like that thing? Is it going to be different? Is it going to be smaller?
It really won't be. 1,000 particles, that's ridiculously small. And if you can have a design where they can be put together, etc., like depending on the approach you use, like there is an approach that uses a technology similar to the MRI, puts a whole bunch of atoms in a fluid, shoots some, like put them in a magnetic field, shoots waves at them, etc. That would be kind of big. That won't work with a laptop. And as a side note, one of the fluids that scientists are exploring right now for this specific design is coffee. So our Kenyan friends start with enough capacity, it might be very useful in the next few years. But basically, you could put that in a chip, in a microchip. You just put that in the motherboard, etc. The laptop will still look like this, maybe. But it will have a lot more computing ability, etc. Yep.
Let's say a software question. Will Windows run on it? Which company is working on that?
Right now, it's not really at the level of companies. It's more of professors, researchers in universities, things like that, that explore different aspects of it. There's not really a company that's right now saying, okay, let us build a quantum computer. Everybody has their way of thinking about it. Every single person has a specific design that they like. I would assume that a lot of firms, big companies, are paying some type of interest on the technology. And that will most likely not be the software companies, not the Windows, not the, I don't know, more like the IBMs, the HP, the Dell. These will be the guys interested in this new thing. But there are prototypes out there. They're still very basic. They just put 2 ions together and single them, etc. They can run basic operations. When the technology came about, when the idea of the technology came about, we were expecting the first working prototype in 2025. It came by in 1998. So it's a field that is growing very quickly. One last question. Yep.
Is it expected to be more or less energy efficient than what we currently have?
It is actually more energy efficient, and that's just why I don't really have the rational opinion.